Good morning, champs. Today, we're stepping back from equations and going one level deeper into how we systematically build them. This is about dimensional analysis, similarity, and why numbers like the Reynolds number appear everywhere in fluid mechanics. We're going to solve a full problem using a Gauss-Jordan style tableau because this is the most systematic and least error-prone way to do dimensional analysis. Once you see it, you won't guess exponents ever again. We start by clearly defining the problem. Assume the drag force on a body depends on density, dynamic viscosity, velocity, and a characteristic length. Our variables are force F, density RHO, viscosity mu, velocity v, and diameter d. Before doing anything else, we convert everything into SI base units. This step is crucial. Force is kilograms meters per second squared. Density is kilograms per meter cubed. Dynamic viscosity is kilograms per meter per second. Velocity is meters per second. Diameter is meters. Now every variable speaks the same language: kilograms, meters, and seconds. Next, we build the dimensional matrix. Each column represents one variable. Each row represents the powers of kilograms, meters, and seconds. This is sometimes called the dimension matrix. We now split this matrix into two parts: the core matrix, also called the kernel matrix, and the rest matrix. The rest matrix simply contains the repeating variables. You can choose different repeating variables, but a good choice makes the physics appear naturally. Here we choose density, velocity, and diameter, because this choice leads directly to the Reynolds number, which is used constantly in fluid dynamics. Now comes the key idea. We apply Gauss-Jordan elimination to the core matrix. The goal is to transform it into the identity matrix. We're not solving physical equations here, we're eliminating dimensions. Each row operation corresponds to combining variables in a way that removes units. Once the core matrix becomes the identity, the rest matrix immediately gives us the exponents of the dimensionless groups. From this procedure, we obtain two dimensionless numbers. One is a normalized force, known as the drag coefficient. The other is the Reynolds number, density times velocity times diameter divided by viscosity. This result is not guessed and not memorized. It falls directly out of dimensional consistency. Finally, we rewrite the result in a meaningful form. The drag coefficient is a function of the Reynolds number. This single statement explains laminar flow, turbulent flow, experimental scaling, and similarity laws all at once. That's why the Reynolds number appears everywhere in fluid dynamics. So champ, this is why dimensional analysis matters. It turns complex physics into structure. And Gauss-Jordan elimination is the cleanest way to get there. Once you master this approach, you don't memorize dimensionless numbers anymore. You derive them.